Hello, welcome to Statics. This is Janet Callahan. I am working on problem 345, taken from Hibbler's 14th edition. I want to put in a good word for Hibbler. This is the best text I've ever encountered teaching statics. So what we have is a bucket that weighs 20 pounds. That's our given load. And we've been asked to find the force in these cables, dA, dB, and dC. And so step number one in all these sorts of statics problems where we are thinking about what's going on is we need to write a free body diagram. So I like to give, I write FBD, it means a free body diagram. I'm doing a free body diagram of the point D. Tell your instructor what you're doing and then do it. All right, so here I am at point D. I have a bucket pulling on me. It weighs 20 pounds. I am feeling support in the DB direction because it goes from D to B. And I observe right away that this is actually just going along the axis of Y. So it's a negative. It's going to be going in the negative J direction, and we'll use that in a moment. All right, this point D, right, that's D, is also feeling an FDC, supporting it up, kind of upward and I guess in the positive Y direction. And then the last thing is it has this force FDA pulling off in that direction. So I'm going to be lazy. I'm going to write C diagram for dimensions because I'm pretending I'm in an exam and the diagram's on the page of the exam, and so I don't think I need to spend my time rewriting that because the diagram is going to be where I'm going to be looking to try to write my vectors, which we're going to do next. All right, next steps are that we need to write those three unknown forces or tensions. We need to write them in Cartesian coordinates. So let's just start. Let's start with the easiest one. FDB, written in vector format, we already noticed that it had nothing in the eye. All of its force was located along the J direction. So I'm just going to write it as that. And I am going to hit my eraser button because that force was all in the negative J direction. And then last, there was no component of it in the K direction. And so let's kind of just go back to that diagram and let me explain to you what I'm saying. What I'm saying to you is that this is the negative J direction, and this force is going in the negative J direction. So that's why I've written all of that force going in the negative J direction. Okay, next off, I would like to consider FDA, the force that takes us from D to A. And I would like to write that in full-on Cartesian coordinates. So FDA will equal, and the vector FDA is going to equal the magnitude of vector dA times, and we have a lot of things to write. So we need to look at the diagram, and I'm going to direct your attention to the picture, and I will write in purple. So as we go from D to A, what do I need to do in the X and in the Y and in the Z in order to get from D to A? So this is where I like to pretend I'm an ant located at D and I have to get myself over to A and I have to think about what to do. And so I'm a stupid ant, so I see a little cord going left, right to left. So I'm going to first just move negative 1.5. And what direction was that? That was in the J direction. Now here I am at B. And I can see sugar up at A, and I'm like, all right, how do I get to A? All right, so um, I am looking at the dimensions along the x-axis, and I see that I I am already at positive 1.5 along the x-axis, and I need to wind up at 4.5 along the x-axis. So I'm going to need to move 3 in that x-axis direction, which is, of course, I. All right, and that is just going to get me that tiny, looks like a tiny distance here, but it's actually 3, and that will put me directly below that point. And the diagram is indeed misleading. Last, what do I need to do along the k direction? Well, it's luckily given to us. We're going to have to just move 3 along the k. So what I have in terms of ijk, I have a 3, minus and a half, and a 3. Let's go ahead and write that in. To make it a unit vector, I must divide by, right? I must divide by 3 squared plus 1.5 squared plus 3 squared, which is equal to 20.25. That is actually equal to 4.5, and I'm going to use that later on, and I'm just kind of writing it here so you can see it all together. So good job, we wrote FDA. We're done with FDA. And now we want to move on to FDC. So the vector FDC will equal its magnitude FDC times the position vector divided by its magnitude. So let's go back to our big picture. We are working now on FDC. So let's think about FDC. All right, we are now in green. To go from D to C, to do that, what is it I need to do along the I? What is it I need to do along the J? And what is it I need to do along the K? All right, so again, what's the sort of easiest thing to think about? I think I need to move that far along the I. How much is that along the I? It's negative 1.5 along the I. Next, I think I need to move out along the y direction this far. How far is this far? Well, I was at 1.5. I need to wind up at 2.5, so that to me looks like 1, positive 1. And last, I'm going to need to move straight up along the j, and that's a positive 3, k. So in terms of ijk, I have a negative 1.5, positive 1, positive 3. I must divide that by the square root of 1.5 squared plus 1 squared plus 3 squared. That is equal to 12.25, which is also equal to 3.5. Alrighty. Never forget the load. The load is what enables you to solve the problem. What is our load? That is our load. The 20-pound hanging bucket is our load. And so I'm just going to write that as load equals, so we have a 0i, we have a 0j, and we have a negative 20 pounds k. All right. So step number 1 was to draw the free body diagram of D. Step number 2, right, was to draw the equations of equilibrium. Sorry, step number 2, I want to restate that, was to write the vectors in Cartesian. And that means, as something in the I, something in the J, something in the K. So step number 3 is now write the equations of equilibrium. And I'm going to add carefully. Be careful with those vectors as well. Just be careful all along these problems. All right, so big picture, let's just look back at what we've already done. And I'm going to use a pale green highlighter to just help us think about these forces. So let's think about the X part of the forces first. So FDB has nothing in the I. It's going to have this contribution from FDA. FDC is going to have this contribution. And this is going to have nothing. That's useful because we're going to wind up with an expression of FDA as a function of a number times FDC. And so it's very worth our while to go ahead and write that equation. So let's do that. So I'm thinking about equilibrium in the X direction. So F equals ma. There is no acceleration. So therefore, we are in static equilibrium. And I have no contribution from dB. I have a 3 over 4.5 contribution of FDA. I have a negative 1.5 over 3.5 contribution from FDC. And I have nothing coming from the load. And so, therefore, I can write that FDA is equal to FDC times, what does it look like, 1.5 over 3.5 times 4.5 over 3, which is 0.6429 FDC. And that is equal to FDA. I'm not going to put a box around that, but I am going to put a circle around that so I can find it in a minute. So that's what summing the forces in the X direction told us, and good, we're moving along. So next thing we can potentially do is we can examine what's going on in the Y direction. So let's go ahead and do that. Oh, darn. Hang on, I didn't mean to do that. So I'd like to now think about these equations in terms of relative to what's going on in the Y direction. So let me just choose a different highlighter color. So in the Y direction, I've got this FDB going on. I've got this negative 1.5 contribution going on from FDA. I've got a positive 1 from FDC and nothing going on from load. So let's go ahead and write it. We're going to need it sooner or later. Let's write it out. When we sum the forces in the Y direction and set them equal to 0 because there's no acceleration, in other words, what I'm saying is that minus FDB minus 1.5 over 4.5 times FDA plus 1 over 3.5 times FDC plus nothing equals 0. Okay? Let's look at Z next, just for kicks. So when we turn our attention to summing the force is in the Z direction and setting them equal to 0, what do we see? So let's kind of look back at our equations. We've got, and now I'm highlighting in purple, we've got nothing going on from FDB. We have this 3 over 4.5 factor of FTA. We have a 3 over 3.5 of FTC, and we have a minus 20 going on from the load. Let's go ahead and write it down. Three over 4.5 FAD plus 3 over 3.5 FDC minus 20 equals 0. All right. So what do we do next? What I'm going to do next is I'm going to turn my attention to that last equation we just wrote. And I'm going to fool around with it. So I'm going to rewrite this as 20 equals 3 over 4.5. And see that FAD? I'm going to use the fact that we've already worked out that FAD is equal to this. So I'm going to plug that in right there. And so here I am putting in 6.6429 FDC, because that's equal to FDA. And now I have my 3 over 3.5 FDC. So now I have only one unknown in this equation, and I can use this to work out that FDC equals 15.56 pounds, or FDC equals 15.6 pounds. And I'm going to put a box around that because that's one of the things we're solving for. And once I know that, right, I can plug that into this, and I can find that FDA equals 10.0 pounds. And that's another one of my unknowns, so I'm going to put a box around that. All right, so where am I? Big picture. I have found my FDA. I have found my FDC. And now I simply need to figure out my FBD. All right, the only equation that had FDB in it was this one right here. So I have to use that equation to find my FDB. So let's go ahead and spend some time working on that equation. Working from the equation that I highlighted in purple, which had the sum of the forces in the y direction equal to 0. I'm going to rewrite that slightly, and here I am writing FDB is equal to negative, don't forget that negative, 1.5 over 4.5 times FDA, but we know FDA, it's 10.0, plus 1 over 3.5 times FDC, but we know FDC, it's 15.56. These are all pounds. Therefore, FBD is 1.11 pounds. And I am done. And to check my work, I've already checked my work, and I don't want to waste your time here, but to check my work, remember, this bucket's in equilibrium. So I should be able to add up my FDB and my FDA and my FDC and my load in 3 dimensions. And they should all sum to 0 because that point D is in equilibrium. All right, thanks for your attention.